Several. It's an understatement. Hey. Let's see. Let me expand that for myself. All right. Let me mark some present here. Let's see. Sasha and Julianne and Nathaniel. Okay, Lydia's there. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. So let's see. I need to do that and line up the board. Is that out of focus? That's better. Autofocus. Okay. So we're going to review Chapter 8, General Bonding Concepts, in preparation for Exam 6. This coming Wednesday would be the 17th. Problems first. Or do I have the honor of just yammering on? Let's see. Nature of the chemical bonds, electron negativities, Octet Rule, polarity of bonds and polarity of the molecules. Wait a minute. We didn't finish the lecture, did we?
Oh, no, we didn't.
Okay.
I think we made it about halfway through the lecture.
I thought we had finished. All right, it'll take me a second to reorient here. I need to eject this one because that's where my PowerPoints are located. This is it. Oh, you know what I did? I did finish the lecture. I put it on Blackboard. Mm-hmm. Yeah, the rest of the lecture is on Blackboard. So what I'll do is try to incorporate that into a review. How about that? Rather than look at slides. Has everybody attempted the problems in the review? Or were you expecting us to finish the lecture? Did anybody realize that I had put the rest of the lecture on Blackboard? Nobody? No? Okay. Well, in that case, I guess I better do it. Okay. Let's start this up. Come on. There you go. So this needs to be oh, that's overlapping. There you go. Okay. We were about ready to talk about the localized electron model. Okay. So, yeah, just picking it up. The localized electron model basically says that electrons are assigned to individual atoms, or they're in a bond, one or the other. So you could have, for every single bond, you have one pair of electrons. So if you have a double bond, that's 2 pair or 4 electrons. Triple bond is 3 pair or 6 electrons. Then if you have any electrons that are not bonded, when you draw your Lewis dot structure, you have any extra electrons, then they have to be assigned to an atom. And remember the way we do that, when we have any extras left over, we start from the outside and work our way in. So we have lone pairs that are assigned to individual atoms and bonding pairs which are shared between atoms. Okay, for this chapter, we're only going to deal with part 1 and part 2 here. Part 1 is we're going to draw the Lewis dot structures for a compound. And then part 2 is we're going to use that to predict the geometry of the molecule. Now, why is that geometry important? Remember, individual bonds can have polarity, right? But you can also assign polarity to the whole molecule. And in order to do that, you have to know the geometry of the molecule. Because, for instance, if you have a linear molecule and you have equal polarity on either side of the central atom, then they're going to cancel themselves out. And the whole molecule then becomes nonpolar. I'll give you an example of that in a minute. Part 3 will come in chapter 9. And we're saving these concepts in part 3 for chapter 9 because we need a whole chapter to discuss them. So for the chapter 8, we're only talking about Lewis dot structures and the Vsepr model of the localized electron model. Okay, the Lewis structure. Did I not describe Lewis structure at all? Okay, no, okay. I'll just assume that I haven't. The Lewis dot structure is based upon the Octet Rule. Some of you may have heard of the Octet Rule, especially if you've had anatomy and physiology. The Octet Rule just says that the ideal situation for an atom, particularly in the second and third period, is to have 8 electrons in its valence shell. And 8 electrons means 2 in the s orbital and 6 in the p orbital. So if you're in the second period, that'll be 2s and 2p. If you're in the third period, it'll be 3s and 3p. But still, you have 8 electrons in either one. That's where the octet comes from. And the reason that these elements want 8 electrons in their outermost shell is it makes them look like noble gases. Okay? If you've got 8 electrons, then you've got full shells, you look like a noble gas, and you're stable. And that's what these elements are tending toward in a chemical reaction. They want to think, in quotes, they want to think that they have an octet. Even if they're just sharing electrons, they still think that that outer shell is complete. And that is one of the driving forces for chemical reactions. Now, the octet rule is for the second and third period. For the first period, you've got hydrogen and helium. They only have s orbitals, right? So they go by the duet rule. They're the only two. Hydrogen's trying to look like helium. So when you get 2 hydrogen atoms together, they share their 1 electron. It makes a duet in between, and they're happy because they think, each one thinks it looks like helium. Whereas fluorine is in the second period, right? So it's going to obey the octet rule. And while fluorine starts out with 9 electrons, only 7 of the electrons are in the outermost shell, right? Because the core is 1s2, right? So the octet for fluorine would be 2s2, 2p5 is where it starts. It wants 1 electron. So if it can get an electron in here, then it has a complete shell, but that makes the fluorine excess 1 electron. So if you have 2 of them, how many electrons do you have in the valence shell? Well, G.N. Lewis devised this little technique for accounting for the electrons in the valence shell of elements. And he said, just take the symbol for the element and place these valence electrons around that symbol, pairing up as many as possible. So with 7, you would have 2 here, 2 here, 2 here, and 1 there. 2, 4, 6, 7. Then if it comes in contact with another one, like that, all you have to do is share these 2 electrons, which forms a bond, and this fluorine thinks it has 8 electrons, this fluorine thinks it has 8 electrons. And you get the bond in between. Okay? And each one thinks it has an octet. Now, the way I like to write them is if there are bonds between elements, then for each 2 electrons in that bond, I write a dash. Right? And then the lone pairs go out here by themselves. And notice that those lone pairs are assigned to individual atoms. Right? We don't smear them over the whole molecule. That comes later. Each one gets its own lone pairs. So for carbon dioxide, it's a little more complicated. How do we find out how many valence electrons are assigned to each element? The easiest way is to look at the periodic table and just count from the left. So if we've got carbon, 1, 2, 3, 4. Carbon has 4 electrons in its valence shell. And we would write the Lewis structure like that. Whereas oxygen is 1, 2, 3, 4, 5, 6. Oxygen has 6. 1, 2, 3, 4, 5, 6. Like that. Now we need to form bonds. Okay, so the oxygen needs 2 electrons to complete its octet. Right? So it could share this electron with carbon and that electron with carbon. Now it has 2, 4, 6, 8. Carbon only has 1, 3, 4, 5, 6, 7 at this point. But this oxygen wants to share those two, well, actually, that. Okay. So now, let me clean that up. We've got these 2 pairs here, these 2 pair here, and then we've got that and that. So this oxygen thinks 2, 4, 6, 8. That one thinks 2, 4, 6, 8. This carbon thinks 2, 4, 6, 8. Everybody thinks it has an octet. So that's carbon dioxide. Now the reason we write it that way, like that, is we're just converting 2 electrons into a dash. So there's 1 bond, there's the second bond. There's 1 bond, there's the second bond. And then your lone pairs. Okay, so that's carbon dioxide. Nitrogen, we go through the same process, and nitrogen ends up with 3 bonds in order to give each nitrogen an octet. I'll let you do that one on your own time. Now, if we're going to do a Lewis dot structure for any element, I gave you that one before. All you do is count across 1, 2, 3, 4, 5 for nitrogen, 6 for oxygen, 8 for neon, it's full. But what if we want to do an entire molecule? Right? So here's the procedure. Those are the steps. It's better if we just do one. So let's try water. So we know water is this formula. How many valence electrons are in that molecule? Each hydrogen only has 1. So this is 2 times 1, and oxygen has 6. So that's 1 times 6 is 6. So 6 plus 2 is 8. So we have 8 valence electrons in that molecule. Now here comes the tricky part. You've got to decide how these atoms are arranged. Generally speaking, the more electronegative is on the inside. Not always, but, and when you have written like this, it's understood that oxygen is in the middle, right? So you put your hydrogens out here, like that. Then you form bonds, okay? Got 1 here, 1 here. That's 2 electrons, that's 2 electrons, so that's 4 electrons. And we have 4 electrons left over. So what do you do with the 4 electrons? You start from the outside and work your way in, placing them evenly around the molecule. Hydrogen can't take anymore, right? It only has room for 2. So these 4 electrons have to go on the oxygen. All right, so that's a valid Lewis dot structure for water. Maybe we got to try another one. How about PBr3? Phosphorus tribromide, right? Type 3 compound. Phosphorus is a nonmetal, bromine's a nonmetal, so we have to say phosphorus, and then how many bromines? Tribromide. Okay? So, first, What do we do? Count up the number of electrons. Valence electrons for phosphorus would be 1, 2, 3, 4, 5. So 5 here. Bromine is 7. Notice when we get down to this level, we don't consider the d orbital because it's full. Okay? That d orbital is full to go from there to here. So we only count, based on the octet rule, we only count those two and these 5. So bromine has 7. 3 times 7 plus 5 is 26 electrons. The way it's written says that phosphorus is in the middle, attached to the bromines. Okay, so now we have 2, 4, 6 electrons in bonds. That means we have 20 electrons that have to be placed. Okay, so you start from the outside and work your way in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we've used up 18 electrons. We've got 2 left over. Why did I stop there? Because bromine has an octet now. Each bromine has 2, 4, 6, 8. So that's why I stopped, and I've got 2 left over. So where do they go? Well, we keep moving inward. The only place they can go is on phosphorus. So those 2 go on phosphorus as its lone pair. That's your valid Lewis dot structure for phosphorus tribromide. How about HCN? What's the name of HCN? CN is cyanide. It's a polyatomic, right? So if it's a gas, it's just hydrogen cyanide. But if we put it in water, there's no oxygen there, so it's hydrocyanic acid. Okay, so hydrogen has 1, carbon has 4, nitrogen has 5. Valence electrons. So we've got 10 electrons. Carbon's going to be in the middle. The way it's written gives us carbon in the middle. Hydrogen here, nitrogen there. So that's 2, 4, 6 electrons left. Okay? 1, 2, 3, 4, 5, 6. Okay. All of our electrons now have been placed. Nitrogen's happy. It has an octet, but carbon doesn't. Right? So how do you make an octet for carbon? You take lone pairs and make bonds out of them. So if we take this one, make a bond, that gives 2, 4, 6. Okay, we're getting there. Carbon's got 6 now, it needs 8. So if we take these 2, make another bond, now carbon has 8, and nitrogen still thinks it has 8 because they're in the bond. Right? So we would write it this way. And there's our 2 extra bonds that we just created, plus the lone pair that we didn't use. So that's a duet for hydrogen, 2, 4, 6, 8 for carbon, 2, 4, 6, 8 for nitrogen. And that's your Lewis dot structure for hydrogen cyanide. Okay. Let's see, there's water, there's phosphorus tribromide, and there's hydrogen cyanide. Oh. Now we need to, let's see, is it time to talk about geometry? Not yet. What I'm doing here is to show you the actual geometry of water, but it's a little early for that. We'll get to that in just a second. Okay. So remember I mentioned difficulties with theories. When you start out, everything's beautiful. But as the more you try to apply a theory, the more chinks you find in its armor. And one of those chinks is every compound that we draw a Lewis dot structure for does not necessarily satisfy the octet rule. Okay? We start from real compounds. This is a real compound, boron trihydride. It exists. It's been characterized. But if we draw a Lewis dot structure, boron is 3 electrons, and hydrogen is another 3 for the 3 hydrogens. So we have 6 electrons. But if we draw the structure like that, 2, 4, 6, we've used them all up. So boron does not have an octet. It is deficient. That's less than an octet, but it's a real compound. So we have to go with it. We have to say some compounds don't have an octet. Now the logical question is, can we go the other direction? Can we have more than an octet? That's less than an octet, and in fact, we can. Sulfur tetrafluoride. Sulfur is in the oxygen group. It has 6 electrons. Fluorine has 7, so that's 28 total. And then we add them together and we get 34 electrons. Well, if we draw the structure, sulfur, and then the fluorines, okay, so that's 2, 4, 6, 8, which is 26 electrons. Then we start placing those electrons around. Each one of these fluorines can have how many more? It's already got 2, so it can have 6 more, right? So 6 times 4 is 24. So you have 2 electrons left over. Where do they go? Well, they can't go on fluorine. They have to go on sulfur. So sulfur now has 10 electrons instead of 8. And it has to be because that's a real compound. It does exist. So why can sulfur take on those 2 extra electrons? Well, consider where sulfur is on the periodic table. Sulfur's here. It's in the 3rd period. What orbitals do you have access to in the 3rd period? Right? In the first one, you have 1s, that's it. In the second one, you have 2s, 2p. In the third one, you have 3s, 3p, 3d. Sulfur is using that d orbital to take up that extra lone pair. Okay? That's the simplest explanation. Arsenic pentabromide is a similar situation. You're going to exceed the octet, not with lone pairs, but with all bonded pairs. So arsenic has 10, but they're all part of the bonds. And arsenic is located here in the 4th period. So it has access to d orbitals as well. Okay. I'm going to let you do those. The evidence is there. see. So what do we do? I used the terminology earlier, a valid Lewis dot structure. We follow the rules, we end up with a dot structure. What if you follow the rules and there are more than one possible structures, right? NO3 minus. Like that. So nitrogen has 5, oxygen has 6 times 3 is 18. That's 20, what did I say? 5 and 18 is 23. But it has an extra one here in the charge. Can't leave that one out. So it has 24 electrons that have to be distributed. Nitrogen in the middle, 3 bonds to oxygens, okay, 2, 4, 6. So we have to place 18 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. They're all placed. Okay? But nitrogen doesn't have an octet yet. And we always trend or tend toward octets when we can. So how are we going to get an octet for this nitrogen? Well, there are 3 possibilities, right? You can take this lone pair and make a double bond here. Nitrogen's happy. But what if you did the same thing over here or over here? You get 3 possible Lewis dot structures. And there they are, right there. Double bond here, or here, or here. So how do you know? You don't. That's one of the failings of the localized electron model. Since the electrons have to be localized on individual atoms or in bonds, then it's possible to come up with multiple structures, and you don't know which one is right. So, remember you have 3 choices. If something goes wrong with your theory, what do? Well, in this case, we modified it. We say, all right, we invented this concept called resonance. These 3 structures are valid, but they resonate with one another. That's what that double barbed arrow is for. They go backwards and forwards. So we can't ever tell which one's which. And remember, when we write them like this, we still have to include the negative charge. So they just resonate back and forth. And that's the best you can do with the localized electron model. Okay, we're going to skip that one. Now, in the case of nitrate ion, each one of those was an equivalent structure. But here's the way you tell whether you have equivalent structures or one is superior to the other. If you have a structure that is superior to any of the others, then you stick with that one and throw the rest out. Okay? So in order to do that, there's this concept called formal charge. It's another way of bookkeeping. Remember earlier, let's see, this is 101. We talked about not formal charge, but my mind's gone blank. Shoot, hate when that happens. It'll come to me. Formal charge is another way to account for electrons. So the concept is we calculate the formal charge for each atom. And the best structure is the one that has the minimum, or the one that tends closest to 0 formal charge. Right? So I need to show you some examples. Those are the rules, but examples are better. So here's a Lewis dot structure for phosphorus chlorate. Right, so we got this one, chlorine, 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 and oxygen. There we go. Okay. Now, how do we calculate formal charge for each one of these? Well, let's start with oxygen. How many valence electrons does oxygen have when it's all by its lonesome? It has 6 electrons, right? Valence electrons. How many does it have now? Well, in order to tell how many it has in the molecule, you add up the lone pairs. They belong to oxygen. 1, 2, 3, 4, 5, 6. And then half of a bond. So if it's a single bond, oxygen gets 1 more. -7 equals a -1 formal charge. Okay? How about chlorine? It normally has 7 electrons, right? So 7 minus 2, 4, 6, and half of that bond is 7. Its formal charge is 0. And all of these chlorines are equivalent, so each one has a formal charge of 0. Okay? Just got one more, phosphorus. How many valence electrons does phosphorus have? 5. Starts off with 5, then in the bond it has 1, 2, 3, 4. Because it has no lone pairs, it gets 1 from each bond. Plus 1 formal charge. Okay, so all the chlorines have 0, oxygen is -1, phosphorus is +1. Okay? Now, notice also that when you add up all the formal charges, they have to equal 0 because there's no charge on this molecule. For the nitrate, if we calculated the formal charge for each one of these oxygens and the nitrogen, they would have to add up to -1. Okay? That's just a rule. If you draw any other structure, Lewis dot structure, with applying the rules, and it's a valid structure, and you come up with anything that's greater than -1 here plus 1 there, or -1 plus 1, any pair like that, then that structure is less likely than this one. This is the preferred structure because it has the smallest aggregate formal charges. Okay. Let's see. For example, if we drew carbon dioxide, we did it this way before. But if we did it this way, we'd still have an octet here, an octet there, and an octet there. But if we did the formal charges, we find that the formal charges for oxygen and carbon are lower than the formal charges here, spread on that. So this is the preferred one. I'll let you do the calculations to satisfy yourself. Now this is precaution, just a word of caution. Formal charges are not actual charges. It's just a bookkeeping scheme. Okay? Oxidation state. Oxidation state is one way that we use for bookkeeping, and this is another way. This works better, formal charge works better for differentiating between Lewis dot structures. You have to be careful also because the Lewis dot structure formal charge method can lead to erroneous predictions. I'm going to make every effort not to give you any that do that. But just be aware. Okay, now that we have valid Lewis dot structures, we need a way to determine the geometry of the molecule based on those structures. And this is the Vsepr model. Vsepr stands for valence, shell, electron pair, repulsion. A lot of big words strung together. This just means that we're only dealing with valence electrons, either as lone pairs or in bonds. And the electron pairs that form those lone pairs or bonds are repelling each other. And since they're all negative, what they try to do is get as far away from each other as possible. That means regular geometric structures. And that's the only way you can minimize those repulsive forces. Now, a caution. Vsepr, electron pair. The method doesn't actually use only electron pairs. It should say Vsegr, electron groups. The reason I say that is when you have a bond, now electron pairs as lone pairs, yes, they act independently. But in the bonding scheme, electron pair could be a single bond, a double bond, or a triple bond. We count each one equally. I'll show you how that works in just a second. Okay. Suppose we have, let's just take an example. Remember water? We drew it like this to begin with. Okay? What you do is find the central atom. In small molecules, no problem. There's only one possibility. This is central. That one can't be central because there's nothing else hooked to it. Oxygen is central. Then you count the number of electron groups. 1, 2, 3, 4. 4 electron groups. How do you arrange 4 electron groups so that they minimize their repulsive effect? The regular geometric, three-dimensional geometric structure for 4 is a tetrahedron. Okay? So a tetrahedron looks like this, like that, like that, like that, that. Right? It's got triangular sides, 4 of them. So that regular structure then will place oxygen in the middle, and then we'll have, back here we'll have a lone pair. Out here we'll have a hydrogen, and a lone pair here. Okay? That's a tetrahedron. Now, what does that mean for the geometry of the molecule? Well, it's not like this unless you can envision the electron pairs going back into the board and the hydrogens coming out of the board. But it's easier to look at it this way. Okay? The reason I say that is this is the electronic geometry. Okay? We want to know the molecular geometry. The molecular geometry, you start with the electronic, and then you cover up the lone pairs and say, what do you have left? In water's case, you have a bent molecule. Okay? So what do we do with that? Well, we want to find out if that molecule is polar or not. So first you start with the bonds. Oxygen is more electronegative than hydrogen by a considerable amount. So the polarity is going to be that direction and that direction. Okay? Then you say, how do these two add up? And the fancy term for that is vector sum. Vectors incorporate direction, so you can't just add up the value of this. Say this was, I don't know, 1.2 difference in electronegativity. You can't just add up 1.2 and 1.2 and say 2.4, because you don't get all of that into that direction. When you vector sum it, you get that as your molecular polarity. Right? You add those two together. Let's take another example. We've already done carbon dioxide. Right? So we have carbon double bonded to oxygen, like that. Carbon's the central atom. How many groups does it have around it? 2. How do you minimize repulsive effects with only 2 electron groups? You have a linear molecule. The maximum distance between them is 180 degrees. Right? So, carbon dioxide is linear, and even though oxygen is more electronegative than carbon, like that, they cancel one another out. So carbon dioxide is a non-polar molecule with polar bonds. Let's see. Bond angle. So what's the bond angle here? Well, for a tetrahedron, it's 109.5 degrees. But since we've got 2 lone pairs up here, what happens with the lone pairs? They're not confined in a bond, so they tend to balloon. These lone pairs balloon out, and they press on these hydrogen-oxygen bonds, and they decrease the value to something like 107 degrees. Right. We'll talk about that in a minute. Any questions so far? Okay. So we have the number of groups in this column. We have the electronic. Let's see. Let's do examples first. Let's put a column in here for examples. And then we have the electronic geometry. And then we have molecular geometry. Got to have this one before we can get that. Okay. So what's the minimum number of groups you could have? Well, you have 1, right? Good example of that is oxygen, right? So it doesn't matter which one is which, you're still going to have a linear molecule. And even if you cover up the electron lone pairs, you're still going to have a linear molecule. So that's really a non-issue. If you have 2 groups, which means you have a carbon, not a carbon, you have a central atom and you have 2 atoms bonded to it, then the electronic geometry would be linear. And if you have any lone pairs and you cover them up, let's see, what's an example? Let's say, well, we just did one, carbon dioxide. Okay. You don't have any lone pairs to cover up, so it's still linear. Let's see. We'll come back to that if we need to. Here we go. if you have 3 electron groups. So you have, say, earlier we did this one, right? Boron trifluoride. If you have 3 groups, and there are no lone pairs here, this is trigonal planar. There are no lone pairs, so it's still trigonal planar. So this would be boron here, there, 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 just like that. If we had any lone pairs in here, right, if you have, let's see, I should have put up here lone pairs. Lone pairs. 0, 0, 0 lone pairs. If you have 1 lone pair, what would that give you? That would give you still trigonal planar electronic geometry, but bent. And if you had 2 lone pairs, it would give you linear, but I don't know of any examples for that one. 4, that's more interesting. So with 4 and no lone pairs, what do you have? You have electronic geometry of a tetrahedron. We're running out of time. Of course we are. We always run out of time. Let me check our schedule. We might have to postpone this exam.
So your kid's getting picked up at about midday tomorrow. So over there about 1 o'clock.
Oh, I'm sorry.
Who is?
We're set up exam 6 is for 22nd.
Sorry.
You probably need to look at
So we're going to have a review on Wednesday. Everybody good with that? Okay.
delicately thing. I haven't seen it. You might need to wrap it up to put it in the van. What's been
I'm not muted.
Yeah. Am I interrupting somebody? Okay, so if we have no lone pairs, then the tetrahedron that forms from the four groups, for instance, carbon tetrachloride, would be also tetrahedral for the molecular geometry. If we have one lone pair, then while we have tetrahedral electronic geometry, an example is ammonia. So ammonia is going to look like this, with a lone pair up here. This gives you a trigonal pyramid. Right? So you cover up that lone pair, what do you have? You have a triangular base with nitrogen at the apex. That's your trigonal pyramid. If you have two lone pairs, we've already done this one, that's water, then your tetrahedron becomes bent. Okay? So I'm going to have to erase some of these and work our way back to the top. What's next? 5 groups. If you have 5 groups and no lone pairs, what do you have? Electronic geometry. You have a trigonal bipyramid. And the same here. Okay, what does that look like? Well, you have this triangular base in the middle, and then you have something up here, and then you have something down here. Okay, so that's 5. 3 around here, 2 there. Let's see if we've got some examples. We have examples. Don't have examples. If we're missing, here's a trigonal bipyramid. If we're missing a lone pair, the lone pair, I mean, if we have a lone pair, it's usually on this position, one of these right here, around here. So what does that give you? Well, with the molecule, with the central molecule in the middle, that gives you here, here, there, and there, which makes it a seesaw. If you have one lone pair. If you have 2 lone pairs, you get a T-shape. Because we put a lone pair here and a lone pair here, that means the molecular structure is there, there, and there. Yeah, there, there, and there. Makes a T-shape. If we have 3 lone pairs, then the lone pairs move to this triangular central part. And then you get a linear molecule. Okay? We only have one more. 6. If you have 6 groups, okay? No lone pairs, 6 groups is octahedron. No lone pairs, still octahedron. Oops. It's not going to show us that one. So what's an octahedron look like? Well, it's got a square. And then it has apex. Like that. Okay, so you got the square in the middle and 2 apex there. Let's see. Oh, we didn't do angles. All right. Get back up and see. Bond angles. Here we go. So let's hold that for a second. Hydrogen cyanide. What kind of molecule was that? Linear, wasn't it? Okay. So the bond angle on that one, and what we mean by bond angle is this angle with the central atom in the middle, right? So we have that bond angle is 180 degrees. That's easy. Linear molecules are all 180 degrees. pH 3. Okay. pH 3 is this with a lone pair. So it's a trigonal pyramid. So what kind of bond angle do you have there? Well, remember, we start out with an electronic tetrahedron, which is 109.5 degrees. But with this lone pair, we have something less than 109.5. Right? So that's the bond angle here. What about SF4? Well, SF4 has 2 lone pairs. No, it has 1, 2, 3, 4. It has 1 lone pair, excuse me. Which means it's going to be trigonal bipyramid. Right? trigonal here, with this one on one end. Actually, this one goes in the center. Sulfur in the middle. Then we have a fluorine up here. Fluorine. And we have a fluorine down here, and fluorine here. So that gives you your seesaw. So what are the angles on a seesaw? Well, you've got 180 degrees here. You've got on the pyramid, on the triangle, you've got 120 degrees. This is 180. Those are the only two. Okay. Let's see here. If we're talking about bond angles, let me see what else I've got to do before I run out of time. That's it. Geometry. Okay. Let's see. Let's go to, oops. Let's go. No. Wait a minute, back up. Okay, that's all right. Here we go. If we react phosphorus pentachloride with chlorine gas, we get a mixture of products. We start with this one, and we end up with some of this and some of this. Oops, excuse me, 6. Right, 6. So the question is, do they all have the same structure? Well, intuition would tell you, no, they don't. But how do we know? You have to draw the Lewis dot structure. This is going to be 7 times 5 is 35, and phosphorus is 5 is 40. 40 electrons. This one's going to be 4 times 7 is 28, and 5 is 33, but it's a +1 charge, so it has to be 32 electrons. We lost one. This one is 6 times 7 is 42, plus 5 is 47, plus 1 is 48. So that's the number of valence electrons we have to position. So there's 1, 2, 3, 4, 5. This one has 4. 1, 2, 3, 4. This one has 6. 1, 2, 3, 4, 5, 6. Chlorines. What we have to do is find out, are there any lone pairs around the central atom? That's the question. All right. So 2, 4, 6, 8, 10. So that means we have 30 left. We have 2, 4, 6. 6 times 5 is 30. 0. So these lone pairs around the chlorine, that's it. So what's the structure? 5 means trigonal bipyramidal. So it's a trigonal bipyramid. No lone pairs, so that's the molecular structure. This one has 2, 4, 6, 8, and that's 24. So 1, 2, 3, 4. let's see, 2, 4, 6 times 4 is minus 24. So these lone pairs, and there are no lone pairs around phosphorus, so the electronic structure will also be the molecular structure, and we have 4, so what do we have here? Tetrahedron. Here we have 6. So 2, 4, 6, 8, 10, 12. So that's 36 electrons, and so that's 6 around 6, so it's minus 36. So all these, phosphorus has no lone pairs in any of these arrangements. So the electronic structure is the same as the molecular structure. So if we have 6 around there, what's that structure? Octahedron. Okay, so each one of these has a different structure. Trigonal bipyramid, tetrahedron, octahedron. So there's your trigonal bipyramid. Here's your tetrahedron. And there's your octahedron. What I forgot was the charges. So you have to draw the charges, like that. Now it's complete. Okay, I got 5 minutes. For this one example of a compound made with a noble gas. Xenon tetrafluoride. They've been kind enough to draw the Lewis dot structure for us. That gives xenon 2 lone pairs plus an octet, 2, 4, 6, 8 in the bonds, right? So xenon exceeds its octet by 2 pair. So what kind of electronic structure will that have? Well, count the groups. 1, 2, 3, 4, 5, 6. So electronic is octahedral, right? What we have to do is decide what's the molecular structure, that is, cover up these. Well, it's not as simple as that, because it just depends on where you put the lone pairs in your octahedron. Right? Do you put the lone pairs around on the square, or do you put the lone pairs up here, like that? If you put the lone pairs around here, they're 90 degrees from each other. And remember, lone pair electrons tend to balloon, right? So they get closer to one another than bonded pairs. So if we put them down here, they're actually 180 degrees apart. That is preferable. That's more stable. So the molecular structure for this system is square planar. Okay? And I'm out of time, I think. Yeah. And we'll have a review on Wednesday. Review on Wednesday, exam on the following Monday. Okie dokie. Let's see. If you're missing any, you need to be sure you've turned in your exam. Let's see, I'm missing Lydia and Cody. Chapter 7, exam 5. Okay? Need to get that to me. Any labs? See if I'm missing any labs. Missing a lot of labs. You better check to be sure if you've got a returned lab. Better still go on Blackboard and look at your grades. If you don't have a grade in there for your lab, then it's missing. And you've got some time, but eventually I'll have to stick a 0 there if I don't see anything. Word to the wise. Bye-bye.